Okay, we are now live for the 7th meeting of this seminar, and the topic today is topological semantics, Heiting algebra semantics, and Tarski, Beth, Kripke, maybe a little bit of pre-sheaf semantics, sheaf semantics at the very end, just to motivate what comes afterwards. And the reading is this short paper by Van Dalen, and then there's supplementary reading. This chapter 5, I guess, of Dummett's book that has a lot of stuff. We probably can't discuss all of that, but it has some of the more philosophical points we will touch on the way. First of all, are there any questions before we get started? Okay, so I was going to follow basically the presentation in Dummett, but I must warn you from the beginning that Van Dalen and Dummett have different conventions for which direction trees grow. For Dummett, trees grow down, so further down is further along in time or further along on the tree, whereas in Van Dalen, time goes up, so higher numbers in the order means later. So if you try to compare, you have to swap the order. Okay, so let me try to say a little bit about what we're trying to do here. We are trying to talk about semantics, both from a classical point of view, but also from an intuitionistic point of view. What is the semantics from an intuitionistic perspective of intuitionistic logic? That's the point. So let's try to remind ourselves how the story goes for classical logic, right? So there we have the Tarski semantics for the classical logic, and we use the truth tables to define the connectives. So this is the, so in some sense, the circular but not trivial interpretation of logic. So A or B is true if A is true or B is true, right? And so then you generalize that because you realize that if you have the interpretations of the connectives in 0, 1, then the algebraic laws that are true are the laws of a Boolean algebra. So you can also interpret classical logic in any Boolean algebra because the algebraic laws are the same as in the particular Boolean algebra consisting of 0 and 1 with the truth table connectives. Okay. So in particular, you can interpret classical logic in the power set Boolean algebra of a set, right? And then you take and to be interpreted by intersection and or to be interpreted by union and not to be interpreted by complement. Okay. So maybe I'll just put on some definitions on the board so we have something to think about. So classically, we have interpretations in a Boolean algebra, and I'll just remind you what a Boolean algebra is because I'm going to interpret some variations of it. But before maybe I do this, how many are in Jeremy's proof theory course? 1, 2, 3, 4. So there's going to be some overlap, particularly with today's lecture, but I hope there will also be some differences. Okay, so Boolean algebra, A is a lattice. So in fact, it's a distributive lattice. Distributive. Lattice with complements. So the distributive lattice, let's say it has a domain M, and for me, a lattice will be bounded, so you have a bottom and top element, and you have a binary join, a binary meet, such that you have complements. So every element A has not A, such that join not A is 1, and I guess maybe follows that A and not A is 0. And then you can define an interpretation of implication A implies B means not A or B. Right? And one more thing I just want to remind you all of is that here I take an algebraic formulation of lattices, but you could also have an order theoretic interpretation of lattices, and you can go back and forth. If you have the algebraic structure, you can define the order A is less than or equal to B if and only if, say, A meet B is A. And if you have a distributive lattice in this sense, and you define the order, then you get a post-set which has finite meets and joins, and which is distributive. And if you have a distributive post-set, then you get an algebraic lattice like this. Okay, so I hope that's fairly well known. Just reminding you about it. Okay, so now we define what should be semantics in this sense of intuitionistic logic. So here we do something else. We say a Heiting algebra is a lattice with binary operation. So the analog of this, such that C is less than or equal to this implication if and only if A and C is less than or equal to B, right? And then there's some things you can prove. If you have such a thing, then this is unique if it exists. And if you have a Heiting algebra, then distributivity follows. So it's another exercise. And let's see. Yeah, any Heiting algebra is distributive. And of course, you should also remark that every Boolean algebra becomes a Heiting algebra under this definition. And every finite distributive lattice is a Heiting algebra because you can take there are two ways to say it. Just because you have in a finite lattice, you will have arbitrary joins, so you can just take this one to be the join of all the C's that work like this in this definition. Of course, if you have arbitrary joins, that would work for an arbitrary complete distributive lattice. Or maybe, certainly for a finite distributive lattice, you'll get this as a Heiting algebra. That's all I want to say at the moment. Okay, so then it's easy to check that you can soundly model the intuitionistic propositional calculus in any Heiting algebra, and by using the meet and join to interpret and or, and interpret this binary connective to interpret implication. Everyone good so far? Okay. So if something is provable, then the interpretation will be the top element of the lattice, right? So and if you have a sequent, then you can interpret the premises by the conjunction of the interpretations, and then if you have a provable sequent, then the conjunction of the premises will be less than, the meet of the premises will be less than the interpretation of the conclusion. Okay. Then there are some theorems that you want out to know, and I'm not going to give the proofs in this. I mean, it's a seminar-style presentation, so I'll leave the following the proofs to you. But in fact, there is a characteristic Heiting algebra for intuitionistic propositional logic. So there's just a single one that suffices to do all this. I mean, once you fix the vocabulary of sentential letters. And in fact, if you have a particular sequence in mind you want to test whether it's provable, then you can check just on a finite sublattice of that Heiting algebra. It will be since it's a finite distributive lattice, it will be a Heiting algebra, but it will not be a sub-Heiting algebra of the characteristic algebra, because the interpretation of implication may be different. Okay. So the corollary of this, of course, is that intuitionistic propositional calculus has the finite model property. Okay, so I hope we're still in the realm of reminding ourselves of this. But just to make it even clearer, so we can do the this characteristic thing is basically the Lindenbaum algebra, and I'll just draw a picture for you. I hope you've seen something similar, but maybe it's good to have a picture in mind. So the Lindenbaum algebra for two sentential letters, P and Q. So you have P here, Q here. Then see, I hope maybe I'll put them a little bit further down. P here, Q. Then we have meet P and Q, which will generally be different from 0. P and Q, of course, implies P and Q. There's also a point here that's incomparable, which represents P if and only if Q. So this is the conjunction of P implies Q and Q implies P. Then we have the join, P or Q. And there's these P and Q implies that they're equivalent. Then we have these two joins here, so this will be P or P if and only if Q. And this is Q or P if and only if Q. Then we have this triple join. So this is P or Q or P if and only if Q. Then there is Q implies P. Of course, if you can check as follows. And then likewise, P implies Q. And then there are just a couple more to go. At the very top of the lattice, of course, we have 1. And the next to the top is P implies Q or Q implies P. And here we have, so this is the join of these, which will be P or P implies Q. And this will be Q or Q implies P. Okay, I think I got it right now. Okay, that's about right. Okay, so then you can check. So this is now a finite distributive lattice, and there's a canonical interpretation of the sentence letters P and Q, namely as this thing and as this thing. And then anything you want to know about provability in intuitionistic propositional calculus, you can check by just evaluating this lattice. Okay, so that's the characteristic finite hiding algebra for the fragment containing 2 letters. Very good. Okay. Let me see. I think I need to erase the board at some point. But before that, I have a little bit of a conundrum. I'm going to leave it on, and then I'm just going to start doing the topological semantics, but then I'll use this as an example as part of the topological semantics in a little bit. Okay, so how do we then go how do we get some more Heiting algebras, Heiting lattices to work with? And one way is to start with a topological space. And this is also nice if you haven't seen it before. Is It's the way that Dummett does it, and it's very good for generalizations to the category theory case and the topos theory case, is you can define a topological space to be a set with an interior operator. So instead of saying that you have a class of opens, which are closed under finite intersections and arbitrary unions and contains the empty set and the whole set, you can have a set together with an operator that takes any subset to another subset that's the interior. And then I think I can write the rules for an interior operator. So put that out here. So today a topological space will be a set X together with an operator J, where J goes from the power set of X to the power set of X, such that J of any subset A is contained in A. That's one thing, and its idempotence of J of A is J of A. J of the whole space is the whole space, and J of an intersection is the intersection of the J's. Okay. So if you have a topological space and you define J to be the interior, then that's true. But also if you have such a thing and with the interior operator, then you can define the opens to be the fixed points. So the A such that JA is equal to A. And it follows from these axioms that J is monotone. So if A is contained in B, then JA is contained in JB. And it also follows that the opens are, here, from this it follows directly that the opens are closed under intersection. And it also follows that the opens are closed under arbitrary unions. Okay, so this is a completely equivalent way to define a topological space. Okay. Let's see.
Can you give intuition for why they're open, or why they're closed under arbitrary union?
Yeah, let me just give the argument. I want to leave at least a little room. Okay, so suppose J of UI is UI, right? And I want to know that the union of the UI is still a fixed point of J. Well, obviously, it's enough to show that that the union of the UIs is contained in J of this union, because the other inclusion is automatic from this axiom, right? But for this, it's enough to show that each UI is contained in J of the UI, because then the union of them is also contained. But UI is equal to J of UI, and then by monotonicity, so this was because UI is open, and UI is contained in the union, so J of UI is contained in J of the union. And that's it.
Is the second line supposed to have a union inside the J?
Yes, the union over I of the
Second
line. The second line. Yeah, that's also, yeah. Okay.
Yep. Thanks.
Okay, so that's the. Okay, very good. And now the observation is that if you have a topological space, then the open sets become a Heiting algebra, and you can say what should be the. You can calculate what is the operation. You know what to do for union and intersection, but you have to give this thing. So if A and B are open, we take this to be the interior of the set of X for which X in A implies X in B. If you're in a classical meta theory, you could of course take the interior of B without A. But this also works intuitionistically, so this is fine. Just take this interior and then you're good. And then it's a theorem of Tarski and let's see, McKinney, that every Heiting algebra embeds into a topological Heiting algebra. So in fact, you also get soundness and completeness with respect to just the topological models like that.
Okay. The opens are cones.
Um,
If you make a Heiting algebra into a topological space.
No. This proof from the embedding theorem. Yeah.
You mentioned that.
I mentioned that there is an embedding theorem by Tarski that every Heiting algebra embeds into the lattice of opens, and I think it's probably you do some order theoretic thing. I don't remember. Okay, but it's easier in the case that you have a finite Heiting algebra. In a finite algebra, it certainly it suffices to take the order topology on the ordered set of joint irreducible elements. So, with the order topology, and the order topology is the things where the opens are the down closed sets, or in the terms of the interior operator, the interior, if you have an ordered set. Yes. If X is a posset, partial ordered set, then you can take J of A to be the set of A's in X, for which for all smaller elements, they are in A. B is in A. And this is the interior operator, and the fixed points are exactly the down closed sets. Okay. And at this point, now we can look in particular at this one, and we can say which are the joint irreducibles here. And so it's the top element. So we need P, we need Q, we need P and Q. We need P if and only if Q, and these two guys. Everything else is a finite join of, so either empty join or a binary join of elements below. And so zeros, of course, is the empty join, but these are not. Okay, so we get a postsets in which the order space is isomorphic to this whole thing, right? If you want to take, say, taking join of these, so let's say you take the join of, you can take another color. So say you want to take the join of this element and this element, right? This will be up here and will correspond to the set of elements below them, and that's the bijection. That this works in the finite case. Okay. So there's a bijection from the opens of the order topology on this partial order of joint irreducibles to this lattice. Okay. So in particular, since we have completeness with respect to finite Heiting algebras, we also have completeness of propositional calculus with respect to topological Heiting algebras. Okay, and that's what I wanted to say. Okay. So now we want to talk about what does this mean, and this comes to the information interpretation. Okay, so if we have such a posset and we can make this order topology, we will make an interpretation that says So say P, a formula, a sentence is true at A, and we're going to write it, write this A and then a forcing sign P, if and only if, under the interpretation, A is an element of the open set represented by P. So we have a post set, and you would define open sets for each of the sentence letters, and then you get open sets for all the propositional formulas. And then, so if you start just with the sentence letters, we get this interpretation that, depending on what P is, so if P is an atomic formula A, then this is just that the element A is in this open set assigned to A. So this is something you start with. And if you have conjunction, then it becomes both have to be true. And versus B. For disjunction, it's the same thing. B. But then the interpretation of implication, so the interesting thing, so we can calculate directly what it is from, luckily I still have this interpretation, right? So because of, this is what it means to be the interior of so I know the interpretation of A, I know the interpretation of B, so that little a is in this J applied to these things means that for all B less than or equal to A, if B forces A, then forces B. So this is the interpretation that comes out of the topological semantics. Okay. Now, the next thing to note is, so now we have soundness and completeness with respect to these finite partial orders. And in fact, it suffices to look at trees by a simple construction that takes a partial order, and then you make a tree that's like the complete initial paths through the partial order, and that has the same interpretation as the partial order. So that's why we can talk about Kripke tree semantics. So if you start with an order that's a tree and you do this, then it's traditional Kripke semantics for propositional logic. Okay, so you'd be familiar. Okay. But there's another variant that's important, and that is the Beth tree semantics. So that's what I want to explain next. So instead of so it somehow interacts with how we philosophically interpret this relation. Do we have to know right away whether an atomic formula is true or not, or is so here in the Kripke semantics, the interpretation is we are at some state of information, and we may or may not advance to the next level of the tree. The Beth semantics is motivated by the following stipulations. Instead of saying we may or may not go to the next node, a smaller node here, we say we are at some time steps, and if there is a tomorrow, then tomorrow will come. Does it make sense? So in the Beth semantics, you think of the possibilities as some tree, and there may be some terminal states, at which point you're just done, you're complete. But it may also be that you're, say, in this state of information, and then you know that tomorrow you'll be either here or here, but you don't know where. Whereas in the Kripke style interpretation, if you have such a tree, then it may be that you're stuck here forever. Okay. So whereas for the Kripke semantics, we just said, well, you have to give the sentence letters an interpretation that is monotone, basically. That's an open set. For the Beth semantics, you say that's not enough. I have to. So Beth. So you still give. You have a tree T, and you have an assignment, a relation between nodes in the tree and atomic formulas P, such that, well, it's still the case that you give open sets in the order topology, so that if B is lower in the tree than A, that means later in time, and A makes P true, then B makes P true. You also have to satisfy the following condition, that if you have a bar for a node, so in this case, so you have all the complete paths starting from a node, and you have some subspecies of the tree, so that you make sure that every time you have a complete path from your node, you end up in the bar, right? So S is a bar for A, and for every B in S, B makes P come out true, then A should also make P true. Because if you know standing at A, and you have some bar S, and so this is for atomic formulas, you stipulate, if I can foresee that whatever happens in the future, so I have this bar for the possible futures, whatever happens in the future, P will be true, then I might as well conclude P now.
Simple question.
Yeah.
So at least in the short notes,
yeah,
it's not required that the bar is after. It seems like it would be like before, after, or any combination.
I don't remember.
No?
I think that's probably a mistake. It has to be whatever happens in the future from that point on.
Oh.
Okay. So now we get a different interpretation. This is still the same, but we change the interpretation of disjunction to say, well, a disjunction is true at A. That just means that I can ensure that there's a bar. There's some S that bars A, and so the analog of this, for any B in the bar, A is true at B, or B is true at B. Okay, and then you prove by induction that then 1 and 2 are true for all compound propositions as well. They become open in the order topology, and you have this upward steps from the, if you have a bar and something is true at a bar, then it's true at the node. Okay. So what are some theorems about this? If you have a Kripke tree, you can make a Beth tree such that a formula is true at the root of the Beth tree, if and only if it's true at the root of the Kripke tree under the corresponding interpretation. So how do you do that? Well, we say that by the interpretation of Beth trees, it may now be that we can stutter if we're at a non-terminal node in a Kripke tree. So we just make a new tree that includes all these stutterings. Make sense? So for instance, so let's take an example. Okay, this. So consider this very simple Kripke tree. So it's a finite tree of just 2 nodes. Obviously, let me just mention this. If you have a finite Beth tree, then it's practically useful for intuitionistic purposes because you just go right to the end because you know you're going to go to the end, and then the logic is completely classical. So say we have this Kripke tree, you can make the corresponding stuttering Beth tree. So you start with the sequence just containing A. And now it may be that you, in the Kripke world, you just go to the next state, and then you're stuck. But then you're at a terminal, so that's fine. You're at A, B. But it may also be that in the Kripke sense, you're stuck at A. So that means, but in the Beth world, we have to move. But we just indicate that by taking a sequence that contains A and then A. And then, of course, you have, if you're stuck at A, you can still either go to B or you can be stuck at A for the next time step. So the tree goes like this, then you have A, B, or you have A, and so on. So these are the corresponding paths according to these movements in time interpretations between Kripke and Beth trees. Okay.
So would every node of the Kripke tree have to have this side branching in the translation between the two? Because you
only the non-terminal ones, but yeah. So there's no side branching corresponding to B. Yeah. Okay. We can also go the other way around. If we, or at least back to topological semantics, if you start with a Beth tree, you can make a topological space out of the space of all paths that go through the tree. And then the basic opens are just the nodes in the tree. And then you make a topological space out of the paths in the Beth tree. And then you get, again, classically at least, you get the same interpretation. Okay. So we have a very good understanding of what happens for propositional logic. So now let's try to go to predicate logic. Okay, so I'm sorry there's not much to discuss at this point, but there's just some setting up to do. And then certainly there will be some discussion about what's the intended semantics of intuitionistic predicate logic. Because you see, for propositional logic, there's not much trouble. You can take Kripke trees, you can take Beth trees, and you have completeness even intuitionistically. You can prove that. So it's not so much of an issue. But if you go to predicate logic, what should be the intended interpretation? Well, one thing you could do is you could say, okay, for a predicate logic, I need a domain. Let's take single-sorted first-order predicate logic. I need a domain of individuals. So, and then the thing that comes to mind is you fix this domain of individuals, and then in your algebraic semantics, you need to now be able to take meets and joins indexed by D. So if you have enough meets and joins in the lattice, you can define so predicate logic. So say M is a height algebra under D area joins and meets, then you can define the interpretation of, say, exists X, B of X. Maybe you need an assignment of elements in the species D for the other free variables. Let's call that theta. And you would just define this to be the join over, let's say, D area joins over the domain of the interpretations of B with the new assignment where X is assigned the value D and you take the interpretation of all x to be the meet where all possible assignments of the variable x to d, and let's suppose you start off by giving subspecies related to every atomic proposition with an assignment from variables in the domain. So that means you give a subspecies of d to the n for an n-ary predicate symbol. Right, so this would make sense, but it doesn't work very well. So let's see what happens. First, want to note that if you take a topological Heiting algebra, is that a okay, impression. If you take a topological Heiting algebra, then it has all possible meets and joins, because we'd say in predicative set theory, you can just take any join and meet you like. So you have this semantics. And classically, we have a completeness result for this kind of semantics. But that doesn't work intuitionistically. And moreover, we would also like to have completed for the smaller class of topological algebras generated by these Postsets spaces. But that fails even classically. So even classically, if you have this kind of interpretation and you just look at Postsets or trees, something that becomes true is this formula. Which is all x. So p is just a sentence letter, and or f of x implies p or all x f of x. Right. So this is true in all Postsets under this semantics, right? Because if you have a Postsets, then the opens are closed not only over arbitrary joins, but also over arbitrary meets. So this means that, okay, so we have to test whether this is true in a Postsets. Well, you can just check because exactly the interpretation of the for all is now just going to be that for all individuals, this thing is true, and then it becomes true. Okay. So now there are two solutions to this. So this is true in Postsets, and I'm going to forestall one of the domains. Right. So this is we just have one domain, and we use this domain to interpret the individuals. So and that already gives a hint of what one of the solutions would be to use variable domains. So,
but this one is not. Do you intend to say that this one is not provable? So it's a problem that it's true.
Yeah, it's not provable. Yeah.
Exactly.
Yeah. So we don't
so
have
it's a problem that it's true.
Yeah. So we've completeness fails, right?
Yeah, exactly.
This is true in all the models, but it's not provable in predicate logic intuitionistic. But of course, I mean, classically, if you add a certain schema of logic that you could always do this, then it becomes characteristic for this new logic. But that's just not intuitionistic logic. It's some other logic that somehow corresponds to intuitionistic logic with constant domains on trees or something. Okay, but one of the solutions is to say, okay, instead let's have this situation that if you have an ordering relation in the Postsets, then now I have to get the inclusion the right way. So now A is more refined than B, so the domain at B has to be included in the domain at A. That means that as we go on in the information interpretation to more refined states, we get more individuals. So this would be one way to solve the problem, and then we can give a counter model to star, and then we can say have just the domain at A, have just one element, and say that f of 0 is true, and then below it have two elements, 0 and 1, that's at B, and here we say f of 0 is true, and now P is also true. Now let's check whether the antecedent is true. Oh, I have to tell you how to interpret the quantifiers in this new case. So now we change the interpretation of
So somehow the sign flip,
yeah.
Is there maybe that the sign should be that since your dA is a subset of dB and not the other way around, so it's not. There's a mismatch between the formula and the picture.
Yeah.
Yeah, that's because
Maybe you flip the A and the B.
yeah, that's what the A and B.
Yeah.
So we have B is larger than A. Yeah. It wasn't intended that it was exactly the same, but this now it illustrates the formula better because in this case A is really less than B, and we have trees going down. So we start at B and then we go to A possibly. So we have to change the interpretation of a universal sentence being true at a node, and now we say this is true if and only if for all more refined states and for all individuals at that state, dB, B makes B D true. Okay, and then we check the antecedent. Okay, so at this state, it is true for all the elements at this stage that f of that holds. And at this state, P holds, so we are good. Okay, so the antecedent is forced at B. Make sense? But what about the conclusion? We still have that disjunction is true in this Kripke style model. If it's true, if the left-hand side is true, the right-hand side is true. But P is not forced here. And for all x, f of x is not forced here, because then it would have to be true at A that both f of 0 and f of 1 was forced, but we don't have that. So this is a Kripke counter model to this thing with the variable domains. So that's one possible solution, to look at these kinds of models with variable domains. And the other solution is the Beth style solution, and that is to say, no.
Ulrich,
yeah.
can I ask a question?
Yeah.
So the variable domains means that at every stage of refinement, as you say, we have the option of adding individuals to the.
That's right. Yeah. But so this is Kripke. Kripke proved this completeness theorem. But Beth says, okay, no, what's happening is not that we should change the interpretation of the universal quantifier and add these variable domains. We should stick to having one domain. But now we have to change the interpretation of the existential quantifier. And we say that A, of course, exists x b of x if and only if there is a bar. Yes, that bar is A, and for every element in the bar, there is an element of the domain, and now it's a constant because the domain doesn't change. So for every element in the bar, there's an element of the domain such that B makes B of D true. Okay, and then we again can make a counter model to this formula. This was Kripke. And here is the countermodel for star in this sense. So it must be an infinite tree, right? Because finite trees are not useful in the Beth semantics. And we do it like this. So at a terminal node, like one of these, so there are a bunch of terminal nodes. So here, f of 0 and then p. And then here, f of 0, f of 1, p. And so we take the domain to be the natural numbers. And then at this node, we take f of 0, f of 1, f of 2, and p. So p is true at all the terminal nodes, and you get more and more of the domain being having f. And of course, since we need monotonicity still, we have f of 0 here, and we have f of 0 and f of 1 here, but no p. 0, f of 1, f of 2, and so on. So on the stem here, the infinite path, p is never true. Okay, now let's check that the antecedent becomes true under this interpretation. So to make a for all thing true, it's just enough to check that for all n in the domain, this disjunction is true at the product, at the top node. But now I have a disjunction, and I can make that true by giving a bar. So I give the bar. So let's say I want to have n, and I want to show that p holds or f of n holds. Well, I just go down here to the state where I have f of n instead of the n's level, and I make this bar. I have color. Let's make a bar in green. Okay, so this is a bar in this tree. It contains the terminal nodes up to this level, and then it cuts the infinite path here. Now, at every point, all the terminal ones, we have p, so that's okay. And I have f of n here in the infinite path, and that goes to the bar there. So this thing is forced at the top node. Now let's look whether the other thing is forced at the top node. Well, that would mean I have a single bar, so it has to cut a bar that makes, where every element makes p or this true. So it has to cut the infinite path somewhere. And at that infinite path, at that node in the infinite path, p is not forced. And it's not true either that for all n, f of n is forced, because only the first n is forced. Okay, so this is a Beth countermodel to this. Okay, so this is therefore was a lot of verbiage from my point, from my side. So let's take a break, and then we'll have I think we'll have more discussion about where we stand after 5 minutes or so. Let me show you. So here's his. Where is this? Show you his calculus. Weakness, yeah. It's a long chapter. Yeah. So this is the thing you get stuck with all of this calculus. This is a multiple succeeding calculus.
Yeah, the refinement, okay, but does he have a procedure to get the quantum order?
Yeah. I don't know how algorithmic it is, but he does have a procedure. I think it's a Beth.
Beth model.
Beth model.
Excuse me, I don't know. With the Predicate clean,
yeah,
you can do a complete constructive completeness.
Yeah.
Yeah.
Yeah. I was going to mention formal topology.
But with this it's not possible. But with back model,
Only with Markov space.
you do Markov principle by out of the weakness.
Yeah, it's equivalent.
And so with one fit topology it's possible.
Yeah.
And but then you mentioned also deductive. Deductive doctrines. Hyperdoctrines.
Oh, hyperdoctrines. Yeah, I can mention that.
Because there's
Yeah, there's. You have a syntax.
but they're not useful to do contramodels. Not these ones to use to do contramodels. That's so the back models.
Yeah. I don't know if the formal.
But how do you do the proof search with this as a there is also the OR. The OR, what is it? No, but this is the left. It's done with this.
Yeah. I think that's why it's important that it's multiple succeeding.
Yes. The only distinction is so I should do it with the multiple succeed. Maybe I don't have to. And then you need the bank model.
Yeah.
The order. Okay. Yeah, because the problem is that they are which branch.
Yeah, that's right. But with the multiple succeeding, you don't have to choose.
I want to do you too in the back model. And you do this. Sorry.
What you do when you then formulate completeness, then you say, if I look for a proof of
You have
just
to
a
put
single.
all zero, but the contramodel
Yeah.
has to validate all the premises and falsify the conclusions.
Yeah.
And the same way.
Mhm.
But you don't. Because it should give a similar decidable.
Yeah, yeah.
And you know how to make it not finite, even classically. Usually when it's because the monadic logic is decidable.
Oh, yeah, yeah.
Predicate, no?
Yeah.
Can you show another question? Sorry. Can you show it by using the search? By these procedures.
But it's actually interesting that you mentioned the monadic practice because it proves that the intuitionistic monadic practice is undecidable.
By using this.
Yeah, it comes a little later.
Strange that I asked the people who do allow them they don't. They should look at the how the only restriction is this. They are all invertible and this.
Of course, if it's a duplication.
They are not invertible.
Yeah.
Thank you very much. Thank you very much.
Just wait for Favonia. Okay. So this was a sort of a tour of various models. But now comes the philosophical question. What really should be the semantics for intuitionistic predicate logic from an intuitionistic viewpoint. And there's no completeness proof for this kind of Beth model. In fact, you can look in Dummett. It's equivalent to Markov's principle. So with Markov's principle, you can, but not without. And in fact, you have a reversal. So if you have completeness with respect to Beth models, then you can derive Markov's principle for at least for primitive recursive predicates or something like that. So let me just mention one thing that has been tried. So when you think about, okay, what should be the semantics of intuitionistic predicate logic such that we have an intuitionistic completeness proof? And one way, since we were talking in the very first lecture about the proof interpretation in terms of constructions, you might say, why don't we try that? Have a theory of constructions such that we interpret the logical constants in terms of this theory of constructions. And this was tried, that was first outlined by Kreisel, and then Goodman investigated this a lot. And in the first edition of Dummett, he says, oh, there's this very exciting new development of the Kreisel-Goodman theory of constructions. It'll probably revolutionize everything. And then now in the second edition, it's just barely mentioned, says, oh, it seemed promising at the time, but now people agree it's not really fulfilling. So you can look up and try to see why there was such hype about this, and then why it turned out to be not so fulfilling in the end.
Do you know how long the distance was between the first and second edition?
77 and 2000 maybe?
So long.
Yeah, more than 20 years.
It was like a year apart.
Yeah, that's like 6 months.
Okay, so the next thing so let's remember how the situation is for the classical mathematician, right? For the classical mathematician, you say, well, the semantics of predicate logic is you give a set, and then for every predicate symbol, you give a subset of the power of the domain, but it corresponds to the arity. And if you have function terms, you also give functions of the right arity from the domain to itself. And let's say for a sentence letter, you just give a truth value, true or false. So you might try the same for, as an intuitionist, you say, well, let's interpret the domain as some species, in Brouwer sense, and a predicate symbol as a subspecies. And what should we do with a sentence letter? Well, it could be a subspecies of the singleton, so basically a proposition, because we can't say that there should be a truth value, but we can still say you give a proposition for every sentence letter. And then, in fact, you can, for every Beth tree, you can give such an interpretation by taking the corresponding spread. We talked about how you could give a space corresponding to a Beth tree. You can from this tree, you can basically read off a spread in the sense we were talking about when we talked about Brovarian analysis. And you can say, okay, this is a spread that I use to interpret the domain. And you can then give an interpretation of the formulas such that for all the lawless sequences in this spread, and it has to be lawless, turns out, you can read Ryan Dummett. And then you parameterize the interpretations of the formulas by lawless sequences, and then the translation at this lawless sequence is true if and only if, and then you have a truth definition for the original formula at the prefix, some prefix of the lawless sequence. Okay, so this is the translation. And then if a formula is internally valid, so valid with respect to all possible species and subspecies and so on, then you show in this way that A is valid on Beth trees, because from a Beth tree you can then make such an internal interpretation. Okay. And then what is done in Dummett is okay, we give a nice multiple succeeding sequence calculus for predicate logic, and we do proof search with respect to Beth's Tableau search mechanism. And then we show that if this semantic tableau in Beth trees, if this search fails to construct a refutation tree, then there is a proof. This is intuitionistically valid. This you can do. But there's a gap between being true in all Beth models and this proof search terminating. And this gap is exactly Markov's principle.
Oh.
And this is analyzed in detail in Dummett. So, but if you assume Markov's principle, then it's true that if a formula is valid on Beth trees, then it's provable. And if you have this completeness theorem, then you can derive Markov's principle. So where do we stand after that? Well, there was some good work in Nijmegen, I believe, by Veldman and de Schwart to modify the Beth semantics and say somehow the problem is caused by you don't know whether you are at a node where falsity is derived. But if you change the semantics to so-called exploding Beth trees or exploding nodes Beth trees, and Dummett also tells in 4 different ways how you can do this, and then you can give a completeness proof. But then the problem is this a faithful semantics for intuitionistic logic? And this has been debated a bit, and I think most people agree that it's not a very useful semantics from an intuitionistic viewpoint. But there's a good intuitionistic completeness proof with respect to the semantics. So, okay. Then another thing you can do, and this is something that Ryan will talk about maybe, or at least part of the solution is to saying, okay, instead of looking at topological spaces like this, point set topological spaces, you can look at formal topologies, and I won't say what they are right now, but if you do that, then you can also get an intuitionistically valid completeness proof. But it's not so easy to construct counter models. It's just, but you can get the, similar to how we had the Lindenbaum algebra for propositional logic, you can have a formal topological Lindenbaum space in the predicate case, and that is characteristic of intuitionistic predicate logic. Okay, and then the final thing is some kind of sheaf semantics. This is something we will talk about, I guess Egbert will talk about toposis. So I don't know how much I want to say at the moment. Well, maybe I just want to wait. Let's just, before we go into that, let's hear from you. What do you think should be the semantics of predicate logic from an intuitionistic viewpoint?
For me, it's hyperdoctrines.
Hyperdoctrines.
And then the other sub classes of model you put, because are just useful to build countermodels. If you find this same procedure that I was thinking, but the general, because with the category theory, you can strengthen the relationship between syntax and semantics by building a category of theories of the calculus you are talking about. You can build a category of models you intended to study and try to see if there is an equivalence.
Yeah.
And this would be stronger than having just a completeness theorem. and they put the equivalencies between the category of theories suitably defined by making morphism as translation, and theories are taught as a logic, basically. So the calculus with inference rules plus axioms.
Yeah.
And then you put as a morphism translations, which are the identity basically on the calculus, but they change the actions. Okay. And then on the other side, you take your category of models, and then you can strengthen the notion of completeness by saying that you want an equivalence.
Yeah.
And if you do that for predicate logic, the only kind of model which satisfy this are Lobia-cited doctrines, because they are an equivalent presentation of syntax in algebraically sense, because completeness is rendered by a joint. So this is my idea of giving an algebraic form of the logic.
Yeah.
It's a different issue to do contra models, and for it you need to find the minimum architecture you need to do that, and basically the most elementary ones, and the more decidable is not, but the semi-decidable ones. So it goes in a different direction.
Yeah.
And then completeness with this. So there are two issues basically. One is the most general form, algebraic form of your logic, which is the equivalence categorically between theories and models, basically. On the opposite of it, there is the proof search of contra models, which is very useful, but it goes in the opposite direction. As soon as you have to test a small amount of objects, the better it is, because you want to look for a semi-automatic procedure to do that. And for it, then, it's important not to look for the most general one, but for the most efficient one.
Yeah.
But is orthogonal to the issue. So I would, and for it, you need to do the proof search and to do the contra model, you need to know the completeness, and that is more a practical, let's say, pragmatic reason.
Yeah. Okay, so just to make sure that it's on the microphone, sometimes people say it doesn't catch at the end of the room.
Oh, sorry, no. But
I'm just apologizing for repeating what you're saying. So the idea is that we look at categorical models, and we look at what's called Lavier's hyperdoctrines, which are a general categorical way of doing first-order logic. And then we say, this is a very general algebraic class of models. And we have completeness for this class. But for completeness, so this is soundness. And this is very useful to have a wide range of soundness. And your important point was that for this class, we have more than just soundness and completeness. We actually have an equivalence between the category of models and the category of theories, probably speaking. So this is a very good set of semantics, but we don't care about this equivalence when we're doing proof search or search for counter models. There we just want a small class of potential models for which we can efficiently do proof search.
Yes.
Okay. Very good. Any other thoughts? See, I had something about the difference between the constant domains and the variable domains that we had in the Kripke models. Dummett says something about allowing the variable domains. It's akin to generalizing from decidable domains or domains with decidable equality to an arbitrary domain. And the example is something like this. room. Suppose that your domain is the subset of the Booleans, so the x and 0 and 1, for which x is 0 or p and x is 1. So this is a typical trick in constructive mathematics. I consider some proposition for which I don't know, that it hasn't been decided either whether p or not p, right? Then in the information interpretation, I might be at a state where I don't yet know whether p holds or p doesn't hold. And in this sense, it looks like the domain is just 0 at this point, even though it somehow contains this ghost. But if I just do the constant domains, I don't see this really. But if I allow myself to have the growing domain, that corresponds somehow to this picture where now, in this case, p becomes decided in the positive sense. I might also have another state where it stays like this. So this is one way to understand what happens in the growing domains. You can keep maybe a decidable domain, but then you have to let it be able to grow over time. Okay, that was one more thing I had to say. So maybe let me just draw up. I had this. We had this idea that we wanted an internal semantics. Right? So one of the things, instead of trying to reinterpret the logical constants or something like that, we use the ordinary logical constants, just like you do in classical logic. But now we just take or whatever our internal intuitionistic interpretation of the logical constants. And then when we interpret predicate logic, we have to, for the domain, well, classically we would say we interpret that as a set, intuitionistically by a species. And then a predicate simple. Here we take a subset. And here we take a subspecies. And let's say we have a sentence simple. So this is a subset of the singleton, which classically is true or false. But here we are forced to say, well, it's just any proposition. Okay, so this is what I wanted to put up for discussion. Whether this analogy is, or what are the features of this analogy, right? When you interpret logic here in this sense, in some sense, it's circular, as Girard pointed out. We have this feature where you say that a formula disjunction is true if and only if A is true or B is true. But in some sense, it's not trivial. There really is a reduction going on. You build the meaning of more complicated formula from the meanings of the smaller formulas. And eventually, you're starting off with something that has nothing to do with propositions. You just have these Boolean values and you connect them. Whereas in this case, it's not circular, but in some sense, it's trivial in another way. You just have an arbitrary proposition for the sentences or for the instances of a predicate simple with some constants. But that's what it means to have a subspecies. You have a propositional function on the power of the domain. And when you do a compound formula in the internal sense, where we don't attempt to interpret the logical connectives, you just say, you just build a new propositions out of old propositions, and it's propositions all the way down. So just want to hear what you thought about the similarities and the dissimilarities between those two cases, or what you have something to say about that. don't have a particular conclusion I want to get to. I just wanted to put that out there. Okay, well, maybe that's what I wanted to put out, but I don't have much more for discussion. Any additional questions about this topic? Yeah.
I would like to tell you, just like to make a comment, namely that the completeness with the point-free topology makes that I know, which was done by Giovanni Sambini in a paper, which is from symbolic logic. I don't remember the year. Actually, if you don't, if you want to be just intuitionistic without taking care of the predicativity, is done by a Dedekind-McNee completion.
Yeah.
This is the key point.
Okay. Yeah.
Then formal topology per se is just a rendering of point-free topology in a predicative sense.
Yes.
So if you want not only to be intuitionistic, but also to avoid the impredicativity.
Yeah.
Yeah.
So the point was that if you want the completeness theorem using point-free topology, you can just take the Dedekind-McNee completion of the Lindenbaum or syntactic of the syntactic space, and then there's a further refinement to do that predicatively as a formal space, but that is just a formal space approximation or description.
The predicative rendering of that.
The predicative rendering of the Dedekind-McNee completion.
In that case, yes, because a formal topology is the category of formal topologies. Impredicatively is equivalent to the category of locales.
Yeah.
Okay.
Yeah. So if you add impredicativity, you don't see the difference anymore, and if you add classical logic, then again,
locales.
Yeah, it's just locales. Yeah. Okay.
I had a question about the hyperdoctrine perspective. So does it also suffice to consider some categories where the subobject lattices can interpret intuitionistic logic?
Subobject, what can you repeat, please?
So can you consider only the sort of case of a hyperdoctrine where you're considering a category with subobject lattices that can interpret first order?
Where the functor...
If you can do it one-dimensional. No, you need to do hyperdoctrine. So I don't know if the question is if you can do the semantics with the one-dimensional categories.
So I'm saying so I guess like for higher order intuitions logic, you can think about toposes instead of like I guess hyperdoctrines are only for first order logic, but there's some sort of weaker notion on a topos where it would make sense to interpret first order intuitions logic.
So a topos viewed categorically is a much stronger notion than first order logic, of course, because it's higher order logic. No, the internal logic of a topos is an higher order logic, even more than second order logic. Is a big, strong logic.
I'm saying a weaker notion than a topos.
A weaker hyperdoctrines.
I think it's called a hiding category. That's. I wasn't sure.
Okay. No, I know that. Okay. So the notion of hyperdoctrine, in a sense, is a two-dimensional notion of categories, because you have a functor which goes from a category of sorts, which in this case for first order has to be only tracked from a power of a domains. You take the domain of individuals, you make powers of it to interpret and variables, let's say. And on that, you make a functor into a small category of categories, and the fibers on each, let's say the value of the functor on each object of the category of sorts has to be, let's say, functions from the domains into a Haltin algebra. So you first start with an Haltin algebra, which is the interpretation of the propositional part, and you do the hyperdoctrine structure just to interpret the predicative part. I don't know if I answer your question. So it's like, I mean, first you start with the interpretation of the propositional part, and then you reach the structure of the propositional part via, let's say, a doctrine, a functor, which is not just a category, but you have to have a category which interprets the variables, and then you need to do a more complicated notion, let's say, of doctrine, hyperdoctrine. And so just we don't have just a category like I think categories is a different structure, is a category whose let's say sub-objects are equipped with the interpretation of first order logic. So it's more like a category for set theory, let's say, not only for logic. It's a more general, it's a more, it's a stronger notion.
Hiding category, I mean, isn't it a weaker notion? Because you can sort of turn a hiding category into a hyperdoctrine by taking the functor from the hiding category to its, which you take.
But it depends on the notion. There are this is notion not fixed. While here hyperdoctrine is already is done in the 60s, for hiding categories it's not a fixed notion. See, you should tell me the definition, and then
sometimes
the
I think categories are defined as those categories whose sub-object give rise to hyperdoctrine.
If it is like that. I know Benno van den Berg and Moordyk that they use the notion of hiding categories or positive hiding categories, but there is more for a more elaborate notion than predicate logic.
But is it the case that we can build a syntactic hiding category from a first order theory?
Yes, of course.
Yeah.
The completeness proof is trivial.
Yeah.
Because this is the beauty.
Yeah.
Because it gives it is an algebraic like in a Boolean algebra, it's an algebraic rendering of classical logic, propositional classical logic. But in the same way, hyperdoctrine or hyperdoctrine is an algebraic rendering of a predicate logic. Once you learn it, you cannot distinguish them. It's just a nice algebraic way. Basically, the point is adjunctions in foundations. If you talk about postsets, you see that any connective is an adjunction. Once you learn that, you're done. Okay. So the basic thing is that what we know is not true for all logics. For predicate logic, intuitionistic and classical one, it's true that any connective is an adjunction. We just have to learn that.
Yeah. So I think the answer was yes. But in a trivial sense. Yeah, so there are these categorical notions, and from then you can trivially build syntactic algebraic models, and then you have completeness in a sort of rather trivial way.
I mean, I guess something that I haven't got my mind around, though, is that it seems like there should be one sort of canonical algebraization of the syntax, but those are actually sort of two notions.
Yeah.
But if you have equivalence in categories, you just have different presentation. But equivalence is the most, how to say, in category theory, the best of the beauty of category theory, in my mind, is that it gives a notion of equality, which is not isomorphisms, but it gives an equivalence. So once you found that the category of theories with isomorphisms is equivalent to the category of models.
Yeah, but it's not the case though that I may be wrong, but the category of hiding categories is not equivalent to the category of first order hyperdoctrines.
No, in fact, the category of hiding algebras is equivalent to the category of theories of propositional intuitionistic logic.
Yeah.
So for it, it's easy to do that. So the category of theories of intuitionistic propositional logic is equivalent to the category of Heyting algebras with morphisms, which are the logical morphisms, not the frame category, not the frame. So the category of locale, which is the opposite of the category of frame, is based on the as objects, Heyting algebra, but morphisms, the morphism which says just the frame structure, which doesn't perceive the implication.
Yeah.
If you take the category of Heyting algebras, whose objects are the same, but morphism preserves all the structure of Heyting algebra, then this category is equivalent to the category of theories of intuitionistic propositional logic.
Oh yes, but
it's easy.
If,
was applying to Heyting categories,
Yeah.
not Heyting algebras.
yeah, Heyting categories.
Heyting categories.
Yes.
I don't know what you mean by Heyting categories, because
Well, we mean the
Heyting
categories. Yeah.
is that the categories for which the subobject functor gives rise to hyperdomain.
I don't know who mentioned this.
Yeah, I don't know the answer. Do you know the? No.
I don't know who defined these categories. I never see.
Heyting categories.
No, I never heard of Heyting categories.
Well, every topos certainly should be one.
Yes, and topos. And for example, algebraic secure is the final Heyting topos usually.
Yeah.
For example.
But it's not enough because you need to put some structure on the base. So you need to put
I think category are defined as regular categories for which the subobject functor gives rise to hyperdomain.
Yes.
So yes, the left and right and so on is fine.
And you still have an interpretation of predicate logic, because if you want to pick a certain object to be the domain, then you still have.
Yeah, but it's not natural. It's more sophisticated because you can get to it by regular completion
Yes.
or by completion.
Yeah.
It's not the most natural one.
It's not the most natural
No.
one.
The most natural one for doing trivially,
Yeah.
for doing triviality detail, is the hyperdoctrine all over here with the where the base category is only Cartesian and the objects, since you do untype the variables here, it's
Yeah.
just one. You just ask that the category of domains, the object of the category, of the base category, are powers of one set, which is your set of individuals.
Yeah. So you have a Labir theory for the
Yes.
term algebra structure, and then you have a hyperdoctrine on top of that
Yeah.
for the predicate levels. But the question was whether one should blur the distinction and take the completion of that to get a single category of the maybe formal quotients of sub-objects of this, whether you can recover.
I think that in general
No, yeah.
it's not the case. I think that I think categories is the subcategory of hyperdoctrines of those who can be represented as subobjects.
Yeah,
And I don't think that we are.
they're not equivalent. Yeah.
I don't think that you can represent every hyperdoctrine as a subobject functor for some.
But I don't know what more you're going for, because for me, I distinguish logic and set theory. And when you speak of one-dimensional categories with something in it, I think of set theories. So I think of comprehension, because in order to connect the fibers with a one-dimensional category, you need to get some comprehension. So this is my intuition.
Yes, but there is a kind of comprehension for predicate logic, namely the definable things.
Yes, but it's, yes, you can do the regular completion.
Yeah.
And then you get a regular category where morphisms, where you have as object the formulas, basically.
Yeah.
And the morphisms are the functional relations.
That's right.
in it.
Yeah.
But I found it not so elementary, let's say. Okay?
Yeah.
More,
And it may require some form of choice, for instance, to go from a functional relation to having a term. Or something.
of course. Yes. But when you do category theory, do have to have a purpose.
I think that is one trivial example of I think category, which is not no. For example, the assemblies of different topos from I think category.
Yeah. Okay, so one.
So point of order, there is a definition of a hypercategory in MATLAB. It contains two meanings that I've never heard of before.
Tell me.
So it's a coherent category in which each base change functor has a right adjoint, which is the universal quantifier.
Yes, but it has to be with the finite product, finite fullbacks, otherwise
It's incoherent. It's included in incoherent.
Yeah, a coherent category has the
Yes. I think that is the if you define hyperdoctrines, these item categories are just the categories for which the subobject factor.
Yeah, that should be equivalent. Yeah.
For which it is the minimum requirement for interpreting first order logic using subobject.
Yeah, I think there was a good point though, that you have to have a purpose when you do this, and we were talking about before that it's good when you want soundness to have a large class of models, and particularly so large that you get an equivalence with the logical notion, and for completeness or for proof search purposes, you want a very small thing. But what you were suggesting was something that's in between, that's not here nor there. It's too small to be. You have this equivalence results, and it's too large to do efficient proof search with, or to have some. It's a good question, but I think we have to cut it off there.
But also because my point of view is that I think categories are there to speak of set theories, because you have this base category which is richer than needed.
Yeah.
And it is something which you need to, with comprehension. You know, comprehension is an adjunction. It can be seen as an adjunction. Yeah. It's very nice. And it projects the proposition, the furthest down, and you control the richness of the base category, which are your sets, let's say, by knowing what happens to the proposition connected to it. So that's why when I think of logic, I think of the doctrine. And when I think of, I think category, I think more of the set theory that you get out of the doctrine. Yeah. Like in HOL or in Frege's notion, no? You start with the logic and you think of naive set theory as your set theory, but then it's contradictory. Then you have to type. To type it means that you enrich the base category. You don't take only domain, the powers of domain. You take a rich category, and so I think category would be that let's say the richer structure to get a set theory. This is my view.
Yeah.
Yeah.
Okay, so certainly we can look forward to hearing about toposes, constructive set theory, formal topology, and point-free topology, and many other topics after the spring break. Okay, so that's cut for today.